All right, so let's talk a little bit about what you should have reviewed with ionic and covalent bonding. So here's a little Venn diagram, which is supposed to be very helpful for you to figure this stuff out. And hopefully now, if I told you where on this diagram would you put the term metal, so something on the left side of the periodic table, left of the staircase, that should occur to you that that is only going to be in ionic bonding, where you will see a metal. There are no metals in covalent bonding. So therefore, if I said non-metal, it's in covalent bonding, but it's also in ionic bonding. So you would want to put non-metal in the middle because there's a non-metal in both ionic and covalent. Now, if I said low melting point, a low melting point occurs because you are not actually breaking bonds. You are just breaking forces between molecules. So this would be a covalent situation. So low melting is what I meant to write, melting point. And that's, you see how that says melting? It's gorgeous, isn't it? All right. Anyway, low melting point is a covalent property, whereas dissolving in water is a property that is ionic. And beyond that, achieving an octet is something that both ionic and covalent do. So achieve noble gas configuration is what they're both attempting to do. And then the other thing we said is that solution will conduct electricity. That is an ionic situation. And there you go. I think that's all we did for that. So low melting point is covalent. Metals are part of ionic. Non-metals are both achieving a noble gas. Oops, there's the last of an E. Achieve noble gas. Configuration is both, and then dissolving in water is ionic, and solution will conduct electricity is ionic. All right, so that's there. So now we're going to talk about Lewis structures, and before we do that, we got to talk about the electron dot configuration, or whatever we call these. Anyway, you need the element symbol, and you put dots for the valence electrons. There's two per side going all the way around. So you want two electrons, north, south, east, and west total. So you can see here on, say, neon, that you have the north, the south, and the east and the west all have two electrons, and that's a full octet that's considered stable. So everything else would have as many as sort of the group it's in. Remember, this is group 1, this is group 2, this is actually group 13, 14, 15, 16, 17, 18, and they all have as many as the ones number from the group. Helium, as you can see, is in group 18, but only has 2. Hopefully you realize that as well. And you can't have more than 8, and we're talking about the SMP. So remember that these are important because when two atoms come to each other, the valence electrons, the outermost electrons, are the ones that are first introduced to each other, basically. So that determines how they react. And that's why if you look up and down, like group 15, they all have 5 valence electrons, and that's why they react similarly. Everything in group 14 has 4 valence electrons. That's why they react similarly. Okay. So let's do silicon. Silicon is atomic number 14. Its electron configurations 1s2, 2s2, 2p6, 3s2, 3p2. You can convince yourself that on a periodic table. So we're looking at the outermost shell, and remember this number here determines the shell number. So those are the only ones we're worried about, the 3s2 and the 3p2. So that's a total of 4 valence electrons. And therefore the Lewis dot would be silicon with 4 electrons around it. And you can couple these or just go around once and then go around a second time. However you want to do it is fine. You will see when we start doing Lewis structures that these Lewis dot notations need to work for you, basically. All right, so here's another example. We have bromine. Bromine's number 35. Its electron configuration is everything argon is: 4s2, 3d10, 4p5. So again, the valence is the 4 level, and it has a total of 7. So that's 7 valence electrons, and the Lewis dot notation would be the element symbol bromine, and then you just put 7 dots going around: 3, 4, 5, 6, 7. So that just shows you when you hit bromine, you have 7 valence electrons. All right, so that should make sense. Now, diatomic molecules, these are the certain molecules that exist as pairs in nature. So that is what a diatomic molecule is. And here are some wonderful depictions of oxygen and nitrogen, which are 2 of the 7 things that do this. This I introduced so that it's hopefully burned into your brain a little bit. The actual diatomic molecules are here: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Turns out they make the number 7 on the periodic table. The problem is there's only 6 of them that make the 7, so you got to remember that hydrogen is 1. The other thing Quigley does is she uses this word Brinkelhoff, so that tells you that it's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So hopefully one of those ways will help you do this. Now, as far as the why this happens, if you consider the simplest hydrogen, so when one hydrogen is created and another hydrogen is created, they're each 1 electron away. Hydrogen's trying to be like helium as the noble gas, so it wants 2 electrons. So when 2 atoms of hydrogen are created, they will see a reason to get close to each other and start sharing these electrons. And they share because they have the same electronegativity. So there's not going to be one being able to pull one away from the other. It's basically twins, which is why this is such a great picture, right? Neither one is going to have the ability to pull that electron away. And as a result, hydrogen will bond with itself as soon as it's created so that it achieves noble gas configuration. Now, that's going to be true for all these halogens as well. Fluorine, if you think about it, has the 7, 4, 5, 6, 7, and then another fluorine is created with also 7. And so they're both just 1 away from 8, so they'll just share these 2 to make a bond, and as a result, have a noble gas configuration. So all of the halogens and hydrogen, it makes sense, hopefully, that they're diatomic molecules because they're all just 1 away from having perfectly shared noble gas configurations. Basically, by sharing 1 electron with the atom that was created right next to it, it will be able to achieve the noble gas that it's trying to, for stability reasons, reach. Now, nitrogen and oxygen, then, what's going on with those 2? And if you consult your electronegativity chart, you will see that they both have among the highest on the entire periodic table. In fact, all of these are pretty high. Chlorine, bromine, fluorine is the highest. Oxygen and nitrogen are up there. So oxygen rather is the second highest on the whole periodic table with 3.5, and nitrogen is 3.0. So those are pretty high electronegativities, and because of that, when they are created, they want electrons so much, and they want to achieve that noble gas configuration for stability so dearly that they will, in oxygen's case, as you can see here, double bond. There's 2 bonds there, and nitrogen will triple bond, and that's a matter of just how many electrons they need to get to their noble gas configuration. So oxygen has 6. It's created with another oxygen that has 6. And so that double bond will occur when those 2 share and those 2 share, and you get a double bond. And the same thing will happen with nitrogen, only with 3 instead of 2. All right. And that's all I have to say about that. That's pretty cool. So we're going to start talking about molecular geometry next. That wasn't as painful as I thought it would be. I hope that was helpful to you, and I will talk to you later.